Okay, announcements and such things. You may have seen the message on that the midterms have been graded. So here are some statistics if you're interested. Um, so not sure what to do with these statistics. It's just what it is. Um, Interestingly, there's no difference between grads and undergrads. There's no statistical difference between the various sections. Um, if you've done more than the average, if your score is more than average, you should be happy. Um, Remember that this is not the point. This is just one thing in your final grade. We'll aggregate across homeworks and exams and projects and everything. So don't get stressed if this exam was not too good. It's okay. There are other things that other ways in which you make up the points. Not everyone is a good test taker. Not everyone is a good programmer. Not everyone is a good mathematician. And it just so happens that this class touches upon all these things, which is why you have many different opportunities for scoring. Um, if there are regrade requests, please use the grade scope regrade mechanism. You have a week for that. And I think we just found out that on Gradescope, your exams are for 99 points. On Canvas, it's for 100. We can fix it either by giving everyone an extra point or by making the Canvas denominator 99. I think the Canvas denominator 99 is that's more for my TA. So that's what we'll do. So the exams for 99 points. Um, any questions or any thoughts about this? Yes?
I was gonna ask, I know it was mentioned on Piazza that the fourth grade will be curved a little.
Yeah.
Do you have any idea about what we should expect for that curve?
It usually depends on the relative performance of the class. So usually everyone ends up doing a little better than they anticipate. Is all I can is the trend I have observed over the last many years. Other announcement: there's a project milestone that's due today. You need to have 2 more submissions on Kaggle and a short report. This is mostly to make sure that you're making sufficient progress. Um, Importantly, it's also to make sure that you're on track for all these other things that are left in the semester. There's a homework 6 that's due on the last day of class. On the same day, there's also a project that's due. The project submission, the final submissions are due on April 22nd, for which you need to submit uh, something on Canvas. There's information on Canvas about what you need to submit. There's a final exam the same week on Friday. Importantly, it's not during the class hours. It's on Friday, April 25th at 10:30, and it will cover everything from and including learning theory. I saw your hand first. Yes. Did I? Oh, yeah, you're right. Fine. Yes, that's an easy. Same thing. Yes. Yeah, there's no, you're not going to get another mystery homework. Yeah, it's homework 5. Homework 5 involves implementing SVM, which we've already covered. You should be able to do. It involves deriving logistic regression, which we'll talk about today, and implementing it, which once you derive it, it should be easy. And there's an extra credit question on neural networks. We'll be covering neural networks starting Thursday. And I think we'll cover enough for you to be able to answer that question even by Thursday. There are some questions on all the perceptrons are considered the same submission, but perceptron with decision tree is considered different. So that's just for the questions on Zoom. Any other questions? Yes. It includes everything. We are so if you remember for learning theory, you hadn't done a learning theory homework for the midterm. So I could ask you more detailed technical questions about learning theory. So assume that learning theory is fully covered for the final. What are we expected to report in the final project submissions? Could you elaborate the required elements in the project report? The Canvas description of the final project report gives you exactly those details. You should be able to describe what the problem is, what you did, what you learned, what you observed, and so on. But there's like a little bit more structure that is described in the Canvas description. On Thursday I can pull it up and we can just stare. You can stare at it in class if you want. Yes.
Is the final to be in this room?
It will be in this room. Yes, it will be in this room on the 25th. Don't show up on the 24th because I won't be here, and there may be another final at that time. So you're welcome to take that class day final, but yeah. Another question on Canvas: do we need to do a comparative study of all models, because you need to give enough detail for me to understand what you have done. You can present the results, and the reason the question shows up is because for the final report, there's a page limit of 6 pages. For some people, 6 pages is too little, and for some people, 6 pages is too much. And I'm assuming a reasonable font size. Don't use size 40. Or don't use size 2. I should be able to read it. I'm noticeably older than you all, and I should be able to read it. So, it doesn't have to go into, you don't need to describe what SVM is. I know what an SVM is. I'd be more interested in knowing your impressions on how your SVM did if you used an SVM, or your impressions on what the data what you learned about the data, what the problem based on how your different models behave and such things. Another question is, just to be clear, the final isn't cumulative, but only covers things after the midterm. The final isn't cumulative. It covers everything after the midterm, plus one thing from before the midterm, namely all of computational learning theory. It will not cover things like, say, decision trees and perceptron. That said, though, remember we talked about generalization in the very first lecture of the semester, and we kept talking about it through the semester. So if I ask you about generalization, that doesn't mean that it's not covered in the final, because it's like a point, it's an important point in the class. So I won't be asking you technical questions about the perceptron mistake bound, for example, for the final, because that's from before. Does that make sense? Other questions? Yes. Almost, except learning theory was officially there for the midterm, right? I didn't ask you too many questions about learning theory in the midterm, but learning theory was part of the syllabus for the midterm. Will the final also be lengthy like the midterm? I aim to please. I will try. I don't want, you get longer for the final. If you look at, you get 2 hours for the final. For the midterm, you got 1 hour and 20 minutes. So maybe if you got 2 hours, the midterm would have been easy, right? I mean, seriously, I mean, if you had another 40 minutes and you didn't have the stress of wrapping up in 1 hour 20, you might be able to get more done. So yes, there's also an agreement on Zoom. I don't know if it's for what I said, but I'll take what I get. Okay, any other questions? If not, we're going to jump back into Bayesian learning. In the last lecture, we looked at the Bayesian criteria for learning, and we looked at these 2 different criteria, maximum a posteriori and maximum likelihood estimation. And the key point was we treat the data set, the existence of the data set, and the choice of the hypothesis as random variables, as events, if you will. And we ask, what's the probability that a hypothesis is the true one, given that we observe the data set? And we construct this probability somehow. And if we take the most probable hypothesis according to this posterior probability, we call that the maximum a posteriori. But that's really proportional to, by Bayes' rule, probability of the data given the hypothesis, which is called the likelihood, times the probability of the hypothesis, the prior probability of the hypothesis, P of H. The prior probability of the hypothesis encodes any beliefs you may have about the hypothesis space before any data came along. So maximum a posteriori estimation involves computing those 2 distributions and finding the hypothesis that maximizes that. Sometimes you have no preference over the hypothesis space before any data came along. no preference is equivalent to saying the prior probability P of H is uniform. If this is a uniform distribution, then that's a constant. So it's as good as not existing in the maximization. So if you do not do that, then simply maximizing over the hypothesis space, just the likelihood gives you maximum likelihood. Maximum likelihood is essentially maximum a posteriori estimation with a uniform prior. And then we looked at one sort of a toy example of maximum likelihood estimation, which involves some light bulbs and such things. And I showed you that you get a result using this process of maximum likelihood estimation. You get a result that you could have guessed without doing any work. The number of light bulbs, the fraction, the probability that a light bulb is not working is simply the number of light bulbs that do not work divided by the total number of tries. And I showed you that you can derive that using maximum likelihood estimation. Today, we are going to use, continue from where we left off. We're going to look at a regression problem. The task involves taking a feature vector x and producing a real number. And let's consider all possible functions that can take a feature vector and produce real numbers. And we'll call those the hypothesis, any such function is called h. The way that we'll assume that the data is generated by first applying the true function f here to get f of x. That's the true label. And then some random noise is added to that. You don't get to see that. You don't get to control the random noise. It's an adversary that draws a random, that draws from an unknown Gaussian distribution and adds that number to f of x to get your label. So you see a pair xi, yi. Now, suppose some hypothesis h was the true function. Some hypothesis h was actually f. If that's the case, you will still not match the data perfectly because your yi was generated by yi is f of xi plus the error term, the noise term, which means that yi minus f of xi will still exist. It's a non-zero term that we know just by assumption is normally distributed from, let's say, some fixed Gaussian distribution. Suppose we assume that this Gaussian distribution has zero mean and some standard deviation, sigma, which we don't have access to. Then the probability that a certain data point can exist is simply probability of observing xi, yi. You can compute it using the Gaussian expression. It's p of y given h comma x is simply this expression here. There is a sort of a technical error here, which I'm going to elide. I'm not going to talk about it. But if you are interested in some details of probability theory and formal definitions of probability, you should be able to spot some mistakes in this slide and also a few slides going ahead. But for our purposes, we are going to pretend that those details don't matter. If you did not spot a mistake, don't worry about it. The probability that a certain data set was generated, a single data point was generated using this function h, if h was the true function, is this expression here. Your data set consists of many such pairs. We can assume that every example was generated IID, independently and identically distributed. So the probability of observing a data set, probability of seeing your entire data set given the hypothesis, is simply the product of the probability of all the examples. But what's this quantity here? This is the likelihood. I can write down the likelihood. But this quantity on the right is proportional to the product of seeing the label given the example, because we are ignoring the way in which xi is generated. Any questions so far? Or if you want to make it more concrete, this quantity is equal to I've just expanded this into this thing here. That should not be any surprise to anyone, hopefully. But think about how we assume the data is generated. An input feature vector xi is picked randomly, and then the true label, the true function is supplied, which means this expression here, p of xi given h, is independent of h. The choice of the feature vector xi does not depend on the point on the true function h. So that quantity is nothing but p of xi because it's independent, which means it does not depend on h. So we don't care about it because we're going to maximize over all possible h. So maximizing probability of data given h, the argmax over h is equal to, I'm going to erase a little, argmax over h, the product right? Let's clean this up a little bit. So we have the likelihood is simply proportional to, for our purposes, the product of all the probabilities of yi given xi and h. But we just computed this as this expression here. So we can plug it in. From now on, all that I'll be doing is algebraic manipulations. We've finished all the sort of technical bits. So any questions about this? So there's a question. Is h of xi the expected value of the hypothesis? No, it's the estimated hypothesis. It's essentially our guess for the hypothesis function. If h is just, we've been doing the same thing elsewhere also. H is some function which we do not have access to yet. And we are hoping that this h will be equal to f. And then we are building this model. If h was equal to f, then p of y given x will be Gaussian. If h was equal to x, if h was equal to f, then the likelihood would be proportional to this expression here. So there's another question. How did we get to the equation for p of y given x? Isn't that the PDF of a Gaussian? It is exactly the PDF of a Gaussian because we assumed right here that the data is generated in the following way. Nature doesn't have to respect our assumptions, but we are going to make this assumption to make our life simpler. An input is drawn randomly before any function comes into existence. We have a true function. Nature has a true function f that it applies to that input to get f of x. A Gaussian noise is added to that label. That f of x is a number. Gaussian noise is added to that number. So the label that we observe is f of x plus the error, Gaussian noise. And if that were the case, and if it is true that h of x, if h of x is f of x, then y minus f of x will be equal to yi minus h of x. If h and f are the same function, then y minus h will be Gaussian. So we can fit a Gaussian to this noise term. Does that answer your question? Which means the probability that we see y, a certain yi, given that the hypothesis h is the true function and the input is x, There is no uncertainty in the value of yi except for the error. So this is basically the Gaussian, the Gaussian expression comes into play there. The PDF of a Gaussian shows up. And that's why we have probability of y given x is the PDF of the Gaussian. Okay, so we have this. Now then the rest of the next maybe 5 minutes is going to be just mechanical manipulation. Our goal is to find a hypothesis. I'm calling that HML for short for maximum likelihood. The maximum likelihood hypothesis is simply the one that maximizes, as the name suggests, the likelihood term, which is equivalent to maximizing the product of this the probability of y given x. I can plug in the Gaussian PDF there. So maximizing that is equivalent to this. What do you do now? Any ideas? I need to solve this maximization problem. Any thoughts? Yes. Take the log. When in doubt, for maximum likelihood, the first thing to guess is take the log. In general, we don't like to have these exponentials in our maximization. Let's work with the log space. And the reason for that is, the reason that is a valid operation is log is an increasing function. So the thing that maximizes the function inside the box, or the thing that maximizes this expression here, the function h that maximizes that expression there, will also be the function that maximizes the log of that expression, because log is an increasing function and it does not change the relative order of these argmaxes, of these the relative ordering of these hypotheses. So then we get the log likelihood. So we can take the log and we can simplify this and we get the log likelihood. Taking the log simplifies things quite a bit because the product becomes the sum. So this product is now this sum over m is the sum number of examples. So we are summing over the data. This quantity here, we take the log of it. So we get log of the thing. And then log of e power minus all that stuff simply shows up as minus that thing there. I want to maximize over all possible hypotheses. But look at this first expression here. That doesn't depend on the hypothesis at all. It's just a constant. I'm going to maximize over a function. I don't need to keep that constant around, so I can get rid of it. And let me move the minus outside. So I can maximize over this thing. Argmax of negative sum over the examples y minus h squared divided by 2 sigma squared. Sigma was the standard deviation of the Gaussian. Computing the argmax of a negative function is the same as argmin of the positive functions. And this sigma is a constant. It's a positive number. Sigma squared is a positive number. I don't need to carry that around. It's just a constant. So I'm left with, you minimize the sum of the squared difference between y and h of x. Any questions? All the way down here is just some mechanical manipulations. The only sort of slightly, there's the one step that requires a little bit of explanation is the jump from here to here. The fact that we're taking log means that it works because it's an increasing function. So the most likely hypothesis, the maximum likelihood hypothesis, is the one that minimizes the sum of the squared differences. I didn't tell you anything about what h might be. I said h is any function that the capital H here, right? This capital H is any function that takes you from a vector x to a real number. That's an extremely large hypothesis space. Let's make our life a little simpler. Let's consider linear functions. So I can have h of x is w transpose x. So then we get the maximum likelihood hypothesis is argmin, the minimum value among all weight vectors of this quantity here. Have you seen this before? Where? What is this? Least mean square. This is least mean square regression. But we didn't invent least mean square regression like this. We just said, imagine that there's an error. The error was if the ground truth was y and the prediction was w transpose x, the difference is the error. I'm going to minimize the squared error just directly. Instead, I could invent the whole thing in a different way by saying, imagine that nature produces your data by applying a function and then adding some Gaussian noise to it. And then we find the function find the hypothesis for which the residual, the difference between y and x and the prediction, is closest to a Gaussian. By doing that, you recover least mean square regression. This is the probabilistic or the Bayesian origin story for this exact same objective. Which means there are two perspectives here. From the loss minimization perspective, we would like to minimize the difference between the prediction and the ground truth, the square difference, which is we define the square loss, and we want to minimize the mean squared loss, which is equivalent to saying we want to minimize the total squared loss. So the Bayesian perspective is we believe that the errors are normally distributed, and then you can apply the maximum likelihood principle, and you recover the exact same mathematical expression. Two different views of the same problem. This is a very powerful idea. When you have a certain problem and you have multiple different views of arriving at the same answer, that means you can, when you see something, one of these things, you can interpret it in both ways. And the interesting thing is not that you can interpret it in both ways. The interesting thing is you can, each of these ways offer you different possible extensions. What else could you do with this? Maybe you don't care about the squared loss. Maybe you care about the absolute value of the loss. It's so easy to invent here in this world. To recover an absolute value here, you can't do that because the square comes because of the normal distribution. Well, you can. It turns out if you want to invent the absolute value, then you assume that the errors come from a Cauchy distribution. It's just another probability distribution. So, but then you need to have that perspective. I showed you maximum likelihood. I could have thought about maximum a posteriori. What if you have a prior distribution over the weight vector? You could do that. Turns out you'll get a different objective, which it turns out has an interesting interpretation in the loss minimization perspective also. We'll see that when we come to logistic regression. Yes.
Does that mean like most Bayesian problems can be reduced to a regression problem?
Oh, you mean to a loss minimization?
Yeah,
I wouldn't go that far. These are two different lenses to so the question was, can most Bayesian perspectives be reduced to loss minimization? Not really. There are certain questions for which the Bayesian perspective gives you non-trivial ways to interpret the problem for more complex problems that have more complex structure. Similarly, for certain kinds of losses, maybe, I'm sure you can invent a Bayesian story there, but it gets more and more difficult. So the more complicated extensions become harder to reconcile. Someone who is very smart might be able to still do the reconciliation, but it becomes increasingly hard, which is why it's always good to have these two sort of lenses to look at the same thing, because if you have it's just these conceptual tools. If you have different conceptual tools to attack the same problem, depending on the specific problem you have, you might be able to attack it using the appropriate lens. I don't know why we are attacking problems with lenses. Let's call them hammers. You have different hammers to attack the same thing. Other questions? So I'll wrap up our introduction to Bayesian learning. It's just another way of asking, what does it mean to learn? And we looked at two different answers. In both cases, we have these two criteria for defining what's the best hypothesis given a data set. In both cases, we define the criteria using a probabilistic perspective, by treating the observation, the fact that you have a certain data set as a random variable, by treating the choice of the hypothesis as a random variable, maximum a posteriori estimation, map estimation. You don't hear maximum a posteriori, the phrase. People just say map estimation. So map estimation involves figuring out the probability of the hypothesis given the data and observing that it's proportional to the probability of data given the hypothesis, which is called the likelihood, times the prior, and maximizing that product over all possible hypotheses. Maximum likelihood estimation assumes that the prior is uniform or irrelevant or unknown. Let's call it irrelevant, and simply maximizes the likelihood. We saw two examples of maximum likelihood estimation with the binomial distribution and the normal distribution. This is you should be able to apply maximum likelihood and map criteria for simple problems. It turns out that it requires some amount of practice. And we'll look at one more instance of this with logistic, actually one instance each for map and MLE with logistic regression. And what I would like you to think about is the commonalities across the different ways in which we apply these criteria. In all cases, we come up with something like a generative story. I believe that the data is generated this way. And then you make some assumptions about some probability distributions. You construct the likelihood term. Each example, the probability of seeing a certain example is something. Then you construct a likelihood term. You assume that all examples are IID. So you multiply all the likelihoods over the data to get a likelihood of the data, given the hypothesis. And then you maximize that. That's the recipe for maximum likelihood estimation. For map estimation, it's almost the same. We'll see an example of instantiating it. Questions on Zoom?